All right, so now I'm going to switch gears. What we talked about until now is pretty much maybe a continuation of the last lecture, but now we're going to actually switch gears and talk about a different model called logistic regression. And to do that, I'm going to present a new problem. Now we're going to do classification instead of regression. And what I mean by that is we're going to have labels that are not continuous, but they are discrete. And in particular here, let's think of this problem of tumor classification, which is we want to predict if a tumor is benign or malign based on its size. So intuitively, this is not a real data set, this is just a synthetic data set. But intuitively here, if the tumor is small, is considered benign. If it's large, then it's maligned. And here's the data set. Again, I'm back to working on only a single input feature X because it's easier to visualize things in 2D. So my input feature X is size in centimeters. So for instance, the first example has 9.63 centimeters. And the label here is a binary label. It's either 1 or 0. Where 1 means is this red dots in here. See, it's all 1. They are all at 1 here. They are maligned. And the zeros are benign tumors. Okay? So if they're small, they're going to be blue. And if they're red, if they're large, they're going to be red. And I only have these two possible values for labels, 1 or 0. And just some new vocabulary. Sometimes people say, it's very common in the literature to say the 0 labels to call them negative examples, even though it's 0. But okay, whenever someone says the negative examples, they want to say the examples that have the value 0 in the data set. And positive examples are the ones with 1s. So if I say that negative example, I mean that it has a 0 label. If it's positive, I mean it has a 1 label. Okay. So, yeah, I should have put some animations here. But let's think about this. Actually, let me clear this slide a little bit. Okay, one thing we could try to do to solve this problem is actually run linear regression. It sounds a little bit odd because you're trying to do linear regression with classification problem, but it's a fair question to ask. Why not using linear regression, right? What happens if you use linear regression in this problem? So we would fit a line, but now we only have y is equal to 0 and 1s. So the data set is going to look like this. So perhaps the best line we could fit to this data would look like this yellow line here. You would try to capture the middle here of these points and the middle of these points and try to adjust to these examples. But what is the problem here? First, perhaps the first problem we can think of is that, well, since this is a line, the predictions that we're going to get from our model edge are real values. So they're not bounded to 0 or 1s. In fact, if I train this line, I could even get negative values as predictions. And I don't want that. I only want to get predictions that are either 0s or 1s. But if I train the linear regression, it would do that, right? For example, I could give maybe a tumor here that maybe is 1, and then it would give me a value of minus something, right, as a prediction. That doesn't make sense in this context because I want to classify either 0 or 1. A negative value doesn't mean anything. In fact, a value that is greater than 1 doesn't also mean anything. And even the values maybe in between here might not mean much because essentially I want either 0 or 1. So, well, that's the first problem. So one idea to solve the problem would be, well, we could maybe define a threshold, right? Say edge of x is going to be equal 0 if, here I should be called a different, maybe I should call this y hat, which is the prediction. So my prediction is going to be 0 if my yx is greater than this threshold 0.5. So I'm dividing the space, the label space in two, and I'm saying if my prediction, let's say if I put an x equals 4, I'm going to get this 0. Maybe 1 here. So 0.1 is less than 0.5, so then I will get a 0 prediction. And if the value is greater than this threshold, let's say if I put an 8 here, then I would get this value, right? This would be about maybe 85 or something, 0.85. If it's greater than 0.85, then it returns 1. This is starting to getting better. Now, so I'm getting a line and mapping it to a binary function that returns either 0 or 1 depending on the value of the prediction. If the prediction is less than 0.5, it returns 0. If it's greater, it returns 1. So this is a good idea, right? And it could work, but there is still a problem, which is this. If I have added a new example here that is red, see how my line would change. So the model in green here is now, it would be the new model trained on the same data set with just one extra example, and see how much it has changed. Now, my decision boundary, and I didn't introduce this idea, but if you look at this vertical line here, this is what we call a decision boundary. Because if you look at we were considering the predictions, right? But if you look at the x-axis, if the values are lower than or less than 6, they're going to be considered 0. This is for this decision boundary, right? For the yellow one. If the values x are less than 6, then my prediction is going to be blue. It's going to be 0. If they're greater than 6, my predictions are going to be red 1, right? But I just added one single example, and now my decision boundary changed completely. Now I'm actually making a lot of errors here, just because one single example. So, in other words, if we try to use a linear regression with a threshold, we still have this problem of being very sensitive to outliers. So if you add extreme values, can significantly skew the decision boundary. They can change this a lot. And it shouldn't change, right? These values clearly a 1. It's like way after these guys. So this model is kind of not being very smart, right? Because it's clearly a 1 here. It's even like further away, right? So, and this model is trying to get this right, it makes all these ones wrong. So this is the intuition why we shouldn't use linear regression for classification, even using this threshold. So what we're going to do is what we call logistic regression, which the name still has a regression in it, but it's in fact a classification algorithm and not a regression algorithm. This is also another classic algorithm from statistics. This wasn't invented like in this modern era of deep learning. This is a more classic statistical algorithm. And now, similarly to linear regression, we still want to find a function, but now we want to find a logistic function, which looks like this. It has this S shape. And I'm going to talk a little bit about it in a minute. But now my hypothesis space is the space of logistic functions. In other words, I'm going to search for logistic functions which have this S shape. And they are formally defined like this. So this letter here is called sigma, right? So the sigma function or sigmoid or logistic function is defined by sigma of z, which is 1 over 1 plus e2 minus z, right? We can write it this way. Our hypothesis is actually this, is edge of x equals to sigma of wx plus b. So we have a sigmoid function, and our z value here is a linear combination of the weights and input values. And why we are doing that? Because we still want to add, so we want a way to tune a logistic regression function, right? So I need parameters. So my z here somehow has to be a function of x. And the simplest thing we could do is, again, do a linear combination of w and x plus b. So I'm still learning w and b. But now I'm plugging, so you can still think of this as linear regression. This is still a linear regression, but now I add on top of it a sigmoid function. So it's the sigmoid of a linear function. It's a composite function, right? It's a function of a function. And it looks like this. And first thing that is very important, it's bounded between 0 and 1. The function itself. So it's this function is defined in this range, 0 and 1. And you'll see that this is also cool because it helps us in interpreting these values as probabilities, and this is important as well. But here is some characteristics of this sigmoid function. It's bounded between 0 and 1, and it crosses the y-axis at 0.5. Okay? So whenever the function here crosses the y-axis, right, the y here is going to be 0.5. And now this is also interesting because see that example we just saw with an outlier. If you had an outlier here, that wouldn't change the model. Because the way this works is, if the z here, and I'm calling z here, which is our linear combination, if z grows, right, our prediction is going to be very close to 1. It's going to get closer and closer to 1. So as the x-axis increases, you get closer and closer to 1. And this growth is very fast. In fact, this is an exponential growth here. So it grows very quickly from 0.5 to 1. Right? You change here about 1, from 6 to 7, it already grew to almost 1. So this is very fast increase rate. In other words, the slope here is very steep. And here the slope is actually smaller. Or the derivative here is very high and here is very low. Because here it grows very fast and here it grows very, very slowly. And the same behavior happens in the opposite direction, but towards 0, right? This function decreases to 0 very quickly. In fact, from 5 to 2 here, it almost reached 0. Okay? But again, it's bounded to 0. So as it goes to infinity, it tends to 0. Any questions? Okay. So here is some visualizations of different linear regression models. Oh, logistic regression models. Here's our hypothesis space. Again, we are looking, we're going to be defining our edge space by those functions there, 1 over 1 plus e to minus wx plus b. If we had w equals to 0 and b equal to 0, then you would have this function here, 1 over 1 plus e to the minus 0, which would be 1, right? So 1 over 2, this would be 0.5. So you would actually get a line here, right? Because you have two parameters 0, you would have a line that intercepts y at 0.5. I'm only visualizing here the changes in w, right? So b's are going to be always zeros, so we can see how w affects the function. So if I had w equal to 1, then this would be 1 over 1 plus e minus x. And I would get this function here that, again, it's centered at 0 because b is 0. So it's centered at 0 here. And as I said, it crosses the y here at 0.5. This will always be the same, okay? If you look at 0.5 here, it will intercept the y-axis at that point. But if I increase w a little bit, now w is 2 instead of 1. Now see that we have squeezed the s a little bit. Right? Actually, not a little bit. I only changed w by 1, and you can see that it became more narrow. Right? So if you increase w, very quickly this function is going to almost look like a step function. It will never be a step function because it's continuous, but you'll get closer to a step function as you increase w. And a step function is this discrete function, right, that does this, where you actually have 90 degrees here. But as you increase w, this is going to approximate this this step function, where here is 0 and here is 1. But what is cool about the sigmoid, that is actually continuous. So here you always have a continuity here. Whereas the step function, it's not at this point, right? What time? Okay. All right. And here is how B affects the shape of the sigmoid. Okay? If you change, now I'm fixing W to 1, and I'm changing the B's. So I'm changing from 0 to minus 5 and then 5. And here what B does, it just shifts the curve on the x-axis. So if B is 0, then the curve here is going to be centered at x equal to 0. But if B is minus 5, because you have this minus here, then your curve here is going to be centered at 5. And if B is equal to 5, then you're going to get minus 5 here. And your curve would be centered here around minus 5. So B kind of like shifts the function on the x-axis. And W squeezes the function if you increase W. All right, so what is interesting about logistic regression is that because it gives us values between 0 and 1, we can interpret these values as probabilities, okay? So here's our logistic regression model. Again, when I write that way, age of x equals to sigma of edge of x plus b, this is the compact version of it, remembering, so you always have to remember what the sigmoid function is, but that notation is a little more compact. So since we are in this domain of 0, 1, we can think of edge of x as the probability that the label is 1. Let's think of this. When I predict edge of 3, if you look in the graph here, edge of 3 is equal to 0.12. What does the 0.12 mean? It actually means the probability of the label being equal to 1. So I can, which is malignant. Right? So I can read this value of 0.12 as this example, x equals 3, has 12% of chance of being malignant. This is how I interpret the results of a logistic regression. And the same for here, edge of 7. If you look at edge of 7 here, I would get a value of 0.994, and that is the probability of y being equal to 1, or the probability of this example being malignant. It's very high, right? The probability of 7 being malignant is very high, it's 94%. So, because we are in a binary classification world here, if we want to compute the probability of a certain example being benign, I can just use the rules of probability, right? Because the probability of y being equals to 0 is equal to 1 minus the probability of y being equal to 1. And this is what our model gives. Oh, this should be a minus, sorry. So even though my model represents probability of the label being 1, I can compute 1 minus that to get the probability of the input feature being benign in this case, but being 0. Questions? Okay. One thing that is important about logistic regression, that even though we are using this sigmoid function that is not linear, it's still considered a linear model. Because, as you can see in this picture, and I'm going to explain what's going on here, it can only separate the space of classes with a line. Okay? And let's look at this more formally. Here is our logistic regression model. So to make a prediction, y hat, we have to use a threshold. And we normally use 0.5 as a threshold. This could be changed, but we normally use that threshold. So it's going to be 1. Our prediction is going to be 1 if the label is going to be 1, sorry, if the prediction is greater than 0.5, and 0 otherwise. So considering the following, imagine now you have a model that is trained on this data set here. And this model has a edge vector 1, 1. So here you can imagine there's a 1 multiplying this x1. There's this 1 here multiplying x2. And then there's this bias term -3 which is appearing here. So imagine I trained this model on this data set and I got this expression at the end. If you now plug this definition or this trained model on our threshold function, right? Now we're going to get the prediction is going to be 1 if x1 plus x2 minus 3 is greater than 0, greater or equal than 0, and 0 otherwise. So this line here, x1 plus 2 equals 3, which is this line you're seeing here, is the decision boundary of the logistic regression. So remember, what is changing the z value is actually a linear combination of the input with the weights. So you still have a linear decision boundary, even though your sigmoid function is nonlinear. Okay, so that's why we also call this model logistic regression. It's called a linear model because it can't learn a decision boundary that is not aligned. So that was all about the hypothesis space. We have logistic functions now that help us doing predictions that look like probabilities. And we use a threshold to decide if the label is going to be 1 and 0. That's it. But now we need to train these models. And to train a model, we need a loss function. Right? Or to training the logistic regression and to train any parametric model, such as logistic regression, we're going to need a loss function. So remember that what we want in a loss function is we're going to give a data set D, and we want to measure how far the predictions edge x of I they are from the real labels, yi. Again, this should be y superscript. So we could try minimum square error here, right? This is now a probability. It's a number between 0 and 1. And this is a number that is a binary number. So this is either 0 or 1. So in theory, it works, right? So we could do something like, imagine if edge of x 1 maybe is equal to 0.9. So if I do that, I'm going to call this y hat. If I do y hat minus y, and now imagine that the y is equals to 1. I could do this, right? And then square this. This would be 0.9 minus 1 squared, which is 0.1 squared, which is 0.01, right? So it gives a value, it's a positive value. So in principle, and this would always be positive because it's squared. So in principle, it's a fair loss function to use. But we don't use it in logistic regression. Theoretically, you can use it. And it's going to work. If you implement your gradient descent with MSE, it's going to run. And it's going to give you a value of WB. The only problem here is that logistic regression, that MSE is not convex for logistic regression. So it's not going to give us a nicely looking convex function like this, like it gave it to us for linear regression. And we want this because this is easier to optimize with gradient descent because we are guaranteed to get to the global minimum if the loss function is convex. But again, MSE is not in this case for logistic regression. So what can we do? Well, we could just close the laptop and go home, but well, maybe we can try something else. And there is a loss function that it is convex for logistic regression, and this loss function is called binary cross entropy loss function. It's a long name, and it's normally written as so the acronym is BCE. And I'm going to try to derive it with you here, so I don't just put the formula in there for you. So logistic regression, let's remember, right, that the logistic regression edge of x gives us the probability of a feature vector x having the label y equals to 1. So formally, you would express this English sentence mathematically this way, right? What is this expression there exactly says what that English statement is saying. Okay, probability of y being equals to 1 given x is equals to edge of x, which is equal to the definition of logistic function. So for the loss function, what we need is a metric that takes the data set D, and then what we want is we want to maximize the probability of yi being equal to given xy. What do I mean by that? If the example D has a label 1, I want this prediction to be close to 1. If the label y has, for example, y2 had label 0, I want this probability to be close to 0. Okay, so this is what I'm writing here. Let's try to build this slowly. So if you want to write down the probability for a given feature vector x of y, we have two probabilities, right? The probability of that label being 1 given x of I, which is the input feature vector, that's equal to the prediction of the model, right? We just defined the model to be this way, so this probability here is equal to edge of x of I. And we just saw this in the previous slide, right? If I want to compute the probability of that feature vector being equal to 0, then I just can use the rules of probability to say that this is 1 minus edge of x of I, okay? And I can nicely combine these two expressions like this. It's a little trick here. It looks complicated, but it's not. Look what I did. I'm multiplying two terms. The first term is this probability here, but raised to the power of edge of I. And the second term is this probability here, the second probability of y equals to 0, raised to the power of 1 minus y over I. Why can we do that? Well, let's think about this. If y of I was equal to 1, then I would have this term here raised to the power of 1, and this second term raised to the power of 0. Right? So then, what's happened is this whole second term would be 1, so what would be left here would be just the first term. And the other option is, if this here was 1, right? No, 0, I said 1. So if this was 0, then this exponent would be 0. So this term here would be 1, and this term would be 1 minus 0 would be 1. So I would have left just the second term. Okay? So this expression is just these two combined. Right now, what we need to do, and this statement here is this statement here in this English statement here on top is this one using probabilities. So what I want to do is I want to maximize this product here, and I'm multiplying each of these products for each example I have. So I want to maximize this probability. That's what I just said. I want to maximize this probability here. Look, it's the same thing for each example in D. So because we're dealing with probabilities, I need to multiply all of them to get the probability of the whole data set. And then to make this a loss function, since these numbers are all probabilities, and I have how do you call it, a sequence of products, right? These numbers, so imagine if I had m equals to 10, and I'm multiplying 10 probabilities. And these are all numbers less than 1. So very quickly, this number goes to 0, very quickly. So I run into numerical issues. If this grows to 100, probably I would already not be able to represent this number with a float. Maybe I would, even with a double, if I use the double float number to represent this loss, again, this would decrease very fast towards 0 because of this sequence of multiplications that are numbers less than 1. So if you think about this, 0.1 times 0.1 times 0.1, this is already a very small number, close to 0. So if you multiply this, if you had the 0.01 here, which is a valid probability, right, this would make it close to 0 even faster. So when you're dealing with probabilities in computer science, we normally take the log of the probabilities. Because when you take the log of these probabilities, then you should just put the log here. Then you can simplify this expression to be equal to the sum of the logs. So if you remember, the log of the product is equal to the sum of the logs. So if I had P1 and P2 here, two probabilities, instead of now dealing with multiplication, I'm dealing with summation. So you see that in computer science, when you're dealing with probability functions, we normally use the log of the probabilities because of that. So we can transform that sequence of products into a sequence of sums. So that's what I just did. And I simplified the equation. So you can do the math at home if you want. But this is the final expression just by taking the logs of this whole expression. And then I'm adding a minus here, because remember, a log of a probability. Probability is a value between 0 and 1. And a log of the numbers between 0 and 1 is negative. Right? So I need to put the minus here. But anyways, I don't want to spend too much time. I just want to give you some intuition of how this loss function came to be. So people had built it based on probability theories. And this is what we call the binary cross entropy loss function. Okay? And this is the function we're going to use for logistic regression. In fact, this is the graph of the function. The blue curve is when your label is equal to 1, and your red curve is for when your label is equal to 0. And you see how you get this nice convex looking function in both ways. So I'm not going to go over this, but this is the partial derivatives of the loss function of the BC loss function for logistic regression. And what is really cool here is that we get exactly the same partial derivatives as in linear regression, both for W and for Y. And because of that, the code for logistic regression is very similar to the code of linear regression, because the gradients here are actually the same. What changes is your model, and obviously your data set. Your data set is going to be a binary classification data set, but your gradients will be exactly the same as we just saw. And that's it that I have for today. Next week, we're going to talk about multi-layer perceptrons, which is our first actual neural network. Okay? Thank you, guys, and sorry for running a little late.